All right, guys, so this afternoon we're going to look at something called Hooke's Law. Okay, and what Hooke's Law tells us, or puts into math terms, I suppose, physics, like the magnitude of the force exerted by a spring is directly proportional to the distance that the spring has moved from its equilibrium point. Okay, so in these pictures, you can see the x equals 0 equilibrium point. And once we stretch or compress a spring, there is a force exerted on, well, whatever you're compressing it with, if it's a box or whatever, right? And so we can see that if I were to write this, I'll do it in black, it's okay. The spring force, right, is going to be equal to negative kx, okay, where x is the displacement okay, and k is a spring constant, okay, and it'll have a units of the Newton per meter, right? That's how much force can be applied, and then we have the spring force. Okay, and keep in mind, I'm just looking at this first picture here, just as a reference. Okay, so you might ask yourself, well, why is the negative here? Okay, well, the negative, we use the word displacement here, which implies direction. Okay, it takes into consideration the direction. Okay, so let's just say here for a sec, I displace this spring, or I push on the spring in the negative x direction. The force, or the spring, is pushing back on that box in the opposite direction. Okay, and so my force value better come out to be positive, right? So if I input a negative x value, like I did in this particular spot, then the force is going to become positive because this negative is going to cancel with that negative. Okay, and that's how that works. Okay, so that's the equation that you can use for a spring force. Okay, and if you would like to, we could add springs into all of the force questions that we've done, where force is equal to ma. You guys know that, and if I just put a little s on there, I'm going to get negative kx is equal to ma. And if I was interested in the acceleration, you would just isolate, right? So you would get acceleration, and because x is displacement, as we saw above, we're going to see acceleration as a vector, right? So the acceleration would be negative kx divided by m. Okay. Now, springs exert forces, but there is also what we call spring energy, right? You can imagine if I push on a spring, we can give it some spring potential energy, if you will, right? Where the spring now has the potential to do work by converting that potential energy, the compressive force that you've put on it, into kinetic energy, right? So as soon as you let it go, that box is going to move. We know with movement comes kinetic energy, right? That's what we're depicting here. So let's say a box is traveling towards a spring, right? The spring is in equilibrium, so it's not contributing any energy to the system at the moment. All the energy is coming from the half mv squared of the box, right? And then it makes contact with the spring, and now we can see that there is some form of kinetic energy because the box is still moving, but we also have this other term in here, and I suppose I should have thrown it in there before I jumped down here. I just got talking. We see what the potential energy for a spring is. And I'll write that back in the box now. We're going to see that the potential energy, you could even call it ES, is equal to 1/2 kx squared. Okay? The elastic potential energy stored in the spring is 0 when the spring is unstretched. Okay? ES, whatever you want to denote it, if you wanted EE or ES, is always a max, right? When the spring is stretched or compressed, proportional to I'm one line ahead. That doesn't belong there. This is always positive. Sorry. Why is it always positive? That makes sense. It's always positive because you've got this. You know that the displacement could be positive or negative, right? Remember, it's displacement. So displacement itself can be positive or negative, but you're squaring it. I'll write it differently. Right? And we know it doesn't matter what sign you have on it. When you square something, it always comes out to be positive, right? So that's what that means. Sorry. I'm a little bit ahead of myself here. Okay, when I completely compress a spring, like in stage, we'll call this stage 1, stage 2, and stage 3, stage 4. If I completely compress a spring, like what I see here, and the box stops moving, now it's all potential, right? So the total energy in this system now is all contributed from the spring. Okay, and then we can see, okay, well, after the box leaves again and the spring goes back to equilibrium, it now has a velocity in the opposite direction of which it started with in stage 1, but it is all now kinetic again. Okay, and so we can use the exact same concepts from the conservation of energy from the standpoint, we could find whatever the energy is going to be at any particular arbitrary displacement x, right? By expressing the total energy as some arbitrary position as. Okay, so we can write this out as like energy before equals energy after. Okay, and we can write something like right. So I'm assuming that we're probably dealing with a scenario like from number 3 down. Sorry, never mind. It's dealing with the motion as it's happening, right? So we're assuming initially that there is no mv squared term because there's no velocity. We're just kind of holding it in place. So no velocity. But afterwards we let it go, and for some arbitrary displacement where the box is still attached to the spring, we're going to see a plus 1/2 kx, kx squared term. Okay, so we have the movement of that box at that arbitrary point in time, as well as any additional potential energy that might still exist because the box is still in contact with the spring. Okay, and that's what something might look like in terms of setting it up in an argument, an energy argument, conservation of energy. If I were to isolate for V, the thing I'm actually interested in, well, we could see that V would equal the square root of sorry, I missed a little x2 there. Okay, the velocity can equal that. The square root of the spring constant multiplied by the difference between the two displacements, all divided by the mass. Okay, and the problem, or not the problem, but the issue, there's one thing missing from here. And it is that because the spring can be compressed and stretched, right, there would be two instances where the velocity could have the same value but opposite magnitude. So let's just say, I'll draw something here, right? We'll say that this box, right, is right here, and it's compressing the spring, right? Well, if it continues to go in, it's going to continue to compress the spring, right? But then at some point, it's going to turn around and come back. But it's going to pass through this point twice, right? And so we know, but you can see here's V1 and here's V2. It's at this point, though, that these two the two velocities, sorry, this box is going to have the same magnitude of velocity, just the opposite direction. So this equation here has to represent both of those instances in time. Well, how do we do that? We know how that's done. You guys would have seen here the v squared, if we had done all the work to isolate, show how we isolated for the v squared, we would have seen v squared was equal to that. And you guys know from grade 10 math, when I square root one side and square root another, you have to include the positive and negative. That takes care of both directions of the velocity, right? Once when it passes through that arbitrary point, on the way as it's compressing the spring, and then as it's going to stretch it out on the way back. Okay? So that would be how we would solve for the velocity of any particular arbitrary point in time. Okay, on the spring. Displacement values of the spring. Okay, so let's jump down. We'll have a look at example 1 here. So a 0.35 kilogram mass is attached to a spring whose constant is 130 newtons per meter. It is free to move on a frictionless horizontal surface. If the mass is released from rest at x equals 0.1, find the force on it and the acceleration at each of those points. Okay, so let's find the force for part A here. So the force, oops, want to erase it. We know that the force for part A, I'll do all the part A's across, okay? So part A, we know the release point is that, right? It's positive, so it's indicating it's being released from the positive spot. So F, the spring force, is equal to negative kx, right? So basically what we got, let's just here for visualization's sake, got a spring. And for the first one, the equilibrium, it does not say. So we'll assume that it's at, we'll call this, I'll draw the equilibrium in. Okay, so for part A, we're saying that we've displaced the box 0.1 meters to the right, in the positive direction. That's why this displacement didn't call it to be negative. Okay. Now, you can imagine if I displace the spring to the right, it's going to want to go back to its equilibrium. So the force being applied to the box is actually to the left, right? And so we should see a negative force. That's what the negative is there for. It's keeping track of what the force is doing, depending on where you choose to displace the box or how if you're stretching or compressing the spring, right? So you're just going to plug in, okay, well, we just want to find the force. What's the force here for part A? Well, the force is going to be, and I'll do the first one a little bit more thorough, and then we'll just jump through the rest, right? So we're going to have, we know what the spring constant is, 130 times the displacement of 0.1. Okay, And if we were to type that into our calculator, you guys could probably do it without the calculator too, but you're going to see that 130 times 0.1 should be 13, right? And you're just going to move the decimal place 1 to the left. Okay, so we know that it's negative 13 newtons would be the force exerted there based on those conditions. Okay, and if we continue to go across, you know, like what happens here? Well, it looks like I've displaced this box half as much, right? And so for part B here, the spring force, if I cut the amount of displacement in half to 0.05, I better expect to see half the amount of force come out. Okay, so I'll do that for this just to prove that it is the case. So negative 130 multiplied by 0.05, right? If you were to type that in, which you can, I'm telling you, we can expect to see what happens. 0.5 times 130, we see 6.5 newtons, negative 6.5 newtons. That's half of this. Well, what happens if I don't displace the box at all? Right? Well, if you don't displace the box at all, you get K times an x of 0. Well, the spring force is 0. It's at equilibrium. Okay, and for the last one, what happens if I push the box to the left? We compress the spring instead of stretch it. Right? Well, the spring force is going to equal, it's still negative kx, but I'm going to see that it's negative 130 multiplied by, this time the displacement's negative. That's why it's a key distinction to say displacement. We're going to see positive 6.5 newtons, right? So we know that the spring force is going to push. You know, you're pushing the box into the spring's pushing back, and vice versa. If you pull the box away, the spring's going to pull it back. It wants to get back to its equilibrium. And we can see that appear in the numbers. Okay. Now the accelerations. We found out what the accelerations would have been in terms of an equation up here at the top. Right? The thing is you guys already found what Fs was, right? So if I was to write this statement down here, you know, so this will be all part I, and part 2 would be like, let's find all the, you would know that Fs would equal to Ma, right? And so we could take Fs and divide it by m, that would equal A. So for part A, we could take our negative 13 newtons and divide it by the mass, which we said was 0.35. That would equal our force. Well, our force here, or spring force, right? Not spring force, sorry. Acceleration. Getting ahead of myself. Right, we can find what the acceleration is if we do 13 newtons divided by the mass. Right? So there you go. Okay, and you just keep going along here until you, I don't know, you'll see that the what happens with the accelerations, right? Should be they're intertwined with the forces that you calculated, right? So if I do part B here, well, I'd see that the acceleration would be equal to negative 6.5 divided by 0.35, right? And for part C, the force in part C we said was 0, right? Because it was at its equilibrium point. So 0 divided by 0.35, well, that's 0, right? I'll do that other one in a sec. We'll make sure that, but we should expect to see that the acceleration value should be half of that. Like something, I don't know, 17.2, I'm just guessing. We could type it in our calculator and see. Okay, it'd be close. Not quite 17. Sorry, it'd be a little higher than 17. But anyway, half. We'll fix that in a sec. Okay, and then over here for part D, we'd see the acceleration would be equal to positive 6.5. So now it's accelerating in the opposite direction. Right, so we should see 18.6, sorry. So we'll see negative 18.6 here and positive 18.6 for part D. Okay. So it just ties things back, right? Like you can use energy arguments or forces. It's applicable in a couple of different scenarios, right? Where we could like springs apply forces, but they also have potential energy. Like if you push something, the same thing. Like a force of gravity with a roller coaster creates potential energy. Same thing. If you compress a spring or stretch a spring, that creates potential energy. The potential to do work, right? As soon as it gets released and gets converted into kinetic energy, we can calculate the amount of work done, right? By looking at the change in kinetic energy. If it goes from 0 to full kinetic, then you know how much work was done in order to do that, right? So let's take a look at example 2 here. Okay, example 2 is I don't know, these questions aren't too bad. Okay, this one's gonna be an energy argument. This one. Okay, so a 13,000 Newton car starts at rest and rolls down a hill from a height of 10 meters. It then moves across a level surface and collides with a light spring-loaded guardrail. Let's neglect any losses due to friction. Find the max distance the spring is compressed, assuming the spring constant is 1 times 10 to the 6 newtons per meter. Missing a couple things here in my question. Okay, so let's first draw a picture. So we've got the car's going to come down a ramp or incline of some sort, and then come across and make contact with a guardrail which has a spring-loaded component to it to cushion the impact, right? So it's not just, that's what the spring's going to do. It's going to decrease the acceleration over some amount of space, or decrease the velocity. So we've got our car. Car is 10 meters above the ground. Right? It has a height. It also has a mass. A weight, not a mass. It has a weight of 13,000 newtons. Okay. So what we could do is we can look at with the scenario, right? So it's going to initially it's all potential energy, right? So we're going to go MGH, right? It's all potential energy. The spring is sitting here at 0 displacement, x equals 0, right? So it doesn't have any energy initially. We let the car go. It rolls down the hill and makes contact with the spring, right? Well, now we'll call the ground 0. Now, afterwards, the only energy in the system is going to be in the spring, half kx squared, right? Because there's no potential because the car is now on the ground, right? And so we can figure out, right? We know what mg is. We don't need the mass. We know what mg is. That's the 13,000 newtons, right? And we know its height initially. What do we want to find out? We want to find out how far the spring is compressed. Well, that's displacement x. So let's isolate for x, okay? So we could say mgh times 2, right, divided by k. That's going to be equal to x squared. You could square root both sides. All right, and then you're going to see, there's your answer. Okay, so we just type in the numbers. Well, we know mg is, so we're going to get 2 times, mg is the 13,000 newtons, multiplied by the 10, divided by 1 times 10 to the 6. And we should see that x, or the distance that this spring is going to be compressed, will be 0.51 meters when you do the math. Okay? It's kind of cool to be able to take something that we were looking at forces and energy. All right. The last question. You have a fish, right? And you're going to hang it from, I don't know if you guys have ever seen these scales, but you can like, the scale is like hooks onto the fish's mouth and then it weighs them, right? And we can see, you know, how much a fish weighs, right? But it also, like, obviously there has to be, I suppose there would be differences between each of those kinds of springs. Like if you bought different ones, they might have different spring coefficients, right? Depending on the spring that they used. But they still have to yield the same answers, right? Like we still have to be able to see what the actual mass of the fish would be, right? And so they have to figure out, okay, well, how do I incorporate the differences in the springs that we're using, company to company, right, in order to give accurate measurements. Okay, for this particular question, I'm not too interested in the actual weight. I want to just find out, you know, how much does the spring stretch, given that you've caught this 1.37 kilogram fish. Okay, and so for part A, we draw a little free body diagram just to keep things organized, right? So for part A, I can draw a spring, and we'll draw a little very boxy fish on this spring, right? And we're going to have the force of gravity downward, and we're going to have, you know, if we're pulling on a spring, then we learned above that the spring is going to pull back, right, in the upward direction. So our spring force is going to be in the positive direction this time, right? Now there's another piece here that I see in question A. It says something about equilibrium. With equilibrium comes no acceleration, right? And so we just want to know how far did this spring stretch to reach this new equilibrium point, right? Well, okay, well, let's say we know with equilibrium, we know the sum of the forces. In this particular question, it's all in the y direction, has to equal 0. So let's look at the forces acting here. Well, we got positive force of the spring, and we're going to have negative force of gravity is equal to 0. Right? And so we can say, okay, well, the force of the spring will be equal to negative kx minus mg is equal to 0, right? And then if I'm interested in solving for x, that's what I'm just going to do. I'm just going to go, okay, well, I'm going to move the mg over. So I'm going to get negative kx is equal to mg positive, right? Divide both sides by negative k. I should see x is equal to that, right? So let's plug in our numbers. We know the mass of the fish, 1.37 multiplied by 9.8. That has to be divided by the k, the spring constant, which we see is 520, right? And that has to be negative. It was negative from up here when we brought it down. Okay, so you just do the math and you'll see that x equals negative 0.0258. Right? And so we know that that is 0.0258 meters down. Okay, now, second part here. So part 1, that's how far it got displaced to reach that new equilibrium. For part B, it says determine the acceleration of the fish after it has fallen 2.05 centimeters. Okay, so just be careful with that because I messed that up this morning. And we're getting some astronomical accelerations. Okay, we want to go, that's going to be 0.0205 meters. Okay, right off the bat, just do that. Okay, and we know, again, if we look at the sum of the forces in the y direction, it's moving this time. We're going to find what the acceleration is, but it's the same argument. There's no additional forces just because it's accelerating. We still have the force of the spring minus Fg has to equal ma, right? And we see negative kx minus mg. If I was interested in the acceleration, I can divide both sides by m, right? What you do to one side, you got to do to the other. There's your acceleration. If you were to plug in your numbers, you'll see negative 520 times, now here's a little catch, it is fallen. Fallen, it means down this distance, so we got to make this 0.0205 minus, again, the weight of the fish times 9.8, all divided by m, 1.37. That's equal to the a value, the acceleration vector, and we will find that a will come out to be 2.02 meters per second squared down. Okay, guys, so that's a little introduction to Hooke's law. It's an application from a force perspective, but also energy, right? So that's that. There's some questions, I believe. I'll have to find the questions and attach them, but I have some questions for you guys to work on as well for this, as well as some solutions to help you. Okay, so let me know if you have any questions. That's that with Hooke's law, and we're almost at the end of your energy portion of the course where we start electricity next, and then that wraps everything up. Okay, so that's that. Let me know if you have any questions, and you guys have a good day.